When you get into model-based definition, you can get it to the engineer within hours versus days or weeks. I'm Pete Marabella. I'm with Metal Finishing Technologies out of Bristol, Connecticut. We're a metal finishing house. We focus on overhaul and repair for aerospace and defense. Model-based definition has an opportunity to have a huge impact on not only how well you can design something and prove it out before you start cutting chips. You also have the opportunity to use that same model to inspect and repair the part. And that's where we're really focused, and we're really excited about what it could do for our customers. When you think about a part that's been in service for a while, you bring it back in, and your idea is we got to get it back into specification so we can return it to service. So the goals of the industry have not changed. When you get into model-based definition, historically you would measure a part against a 2D blueprint, and now we're just collecting a lot more information, storing it, organizing it, making it searchable. You're getting the information real time, and you've taken a lot of the labor out to gather that. So now we've got a good diagnosis. Now the engineers, whoever the owner of the part is, can make a decision, and you can immediately move to the repair. You're taking something that could take weeks down to days. And that's really when you start to get leverage. I think there's great opportunities throughout the life cycle of a part to really have an impact, to understand where the part is, be able to get quicker turnaround times when it comes time for repair, and then be able to extend the part life. I think those are so important because at a time right now when there's a shortage of minerals and things like that, if you can take a part and extend its life, you can repair it and return it to service. So much better for the environment, so much better on lead time, and your fleet availability, which any OEMs that are listening or any operators will know, that is really critical to the success of any enterprise, whether it's military or commercial.
Whether it may be for first article inspection or maintenance, repair, and overhaul, as Peter from Metal Finishing Technologies was sharing, using model-based definition for inspection can be really versatile and work with many of the different inspection processes within your company. I'm Jackie Garofano, Chief Technology Officer of CCAT, the Connecticut Center for Advanced Technology. We're bringing to you a series of videos all about model-based definition. In our first video, we had showed you how to create an MBD file, and in the second, how to then create CNC toolpaths for your machining operations. And now for our third video, Nasir and our team are going to take you through using MBD for inspection. For this, the tool of choice will be structured light scanning.
Thank you, Jackie. Now we're going to take you through using that model-based definition file to set up your inspection process. In this case, we're going to be using structured light scanning to do the inspection on this part. We're going to be walking through taking the MBD file, opening it up in Geomagic control software, and then showing what needs to be done in order to set up an inspection program. We'll be importing the SOLIDWORKS file with all the PMI, and we'll walk through how to set up the inspection template. So within SOLIDWORKS, I have my file open, and there are a couple things that I can do to prepare the file. We can go ahead and just save the SOLIDWORKS native file with all the PMI. In addition, we can go ahead and save out a Step 242 generic file format. So if we go over to the MBD tab, and all the way to the right, we have a function to publish Step 242. In this case, I'll keep the name the same, make sure that the Save As type is set to Step 242, and then go ahead and hit Save. And it will actually jump through some of the 3D views while it's saving that particular format. Within SOLIDWORKS, if we want to go ahead and set up our inspection template, we can do that using SOLIDWORKS Inspector. So what we're going to do now is go into the SOLIDWORKS Inspection tab, and we're going to set up our ballooning function. So in SOLIDWORKS, if we go over to SOLIDWORKS Inspection, we can create a new inspection project. If we click on the button at the top left, we have several templates that we can choose from. We're going to go ahead and stick with the ANSI B4 template. Click the checkbox. And at this point, I have a dialog that allows me to put in information about my part. So this particular part, we're just going to call it MBD demo. part revision is 10. And I have some options on how I want my characteristic info to be calculated. So we're going to start with balloon number 1. We'll sort it clockwise. So through the model, it'll balloon all of the geometric dimensions and tolerancing that we've put onto the SOLIDWORKS file, onto the CAD file in a clockwise fashion. And we're going to leave all the other defaults. So we'll go ahead and hit the forward button or the next button. And here we can choose what we want to include and what we want to disclude from being ballooned. We'll leave the defaults, click the next button, and then we get to the point of setting up our tolerance settings. We could set up our types by precision or by range, and you could see here that we have a couple of different tolerance ranges set up. So we're going to go ahead and hit the checkbox, and what SOLIDWORKS will do now is go through each of our views, and it will actually balloon all of the PMI that we have put onto our model. So here you can see that the system is done doing that, and if we go ahead and rotate our model, now each one of our callouts have a identifier associated with it. If we go into the SOLIDWORKS inspection tab in our model tree, you can see that we have an ID number, a characteristics number, the type of geometric dimension and tolerance that is, and the specification, so the image that it grabbed along with the tolerance. In this case, we have 21 unique ID numbers. This sets us up for creating the inspection template. So the next step, if we go up into the SOLIDWORKS inspection tab, there is an option to export to Excel. What this function allows me to do is select from one of my templates. We have a CCAT process performance sheet template already set up. We're going to go ahead and check that on and hit the checkbox. This will open up a Save As dialog box, and we can go ahead and name the file. We'll name it the file name that we have set in SOLIDWORKS. Go ahead and hit Save. And then SOLIDWORKS Inspection will go through and create my Excel inspection template. So here, we're bringing up the Excel sheet, and you can see that we have our character number, the nominal value, the upper limit, and the lower limit for each one of the geometric dimension and tolerancing that we placed onto our features on the 3D CAD model. What we'll walk through now is taking this model-based definition file and running this through Geomagic Control X to do the same thing. We'll see how we can reuse the data that gets imported and set up our inspection template within Geomagic Control. If we go ahead and launch Geomagic Control, we previously saved the native SOLIDWORKS file. We can go into the menu, File, and we want to use the Import PMI function. This allows us to select the native SOLIDWORKS file. So as you can see, all of my PMI came in along with the 3D geometry. A quick check, we have all the datums were imported. They're pointing to the correct surfaces. I have my basic dimensions, my center slot feature, the length, width, and height of the notch feature in the back of the part, and my surface profiles for the pockets. At this point, our inspection project is fully set up. There's nothing additional that I have to do. As you can see, all of the PMI that came in essentially sets up our inspection project. There's no additional work I have to do. The only thing that I really want to do now is identify each of the measurements with its specific characteristics. To do that, I'll go into my 3D GD&Ts, expand that out, and I can go ahead and click on each of the name and rename the feature. So in this case, I'm going to make the first linear distance identified as characteristics 1, the second as characteristic 2, and I'll continue that for all the measurements that I have on my 3D CAD model. At this point, I'm going to go ahead and save my file, and then set up my inspection template. If I go over into the Home tab, all the way on the right, I can generate my report. And we're going to take away any unnecessary data that we don't have to see. So we're going to leave only the 3D GD&T and remove all of the other visual components of the report. We're going to give this a title of MBD Demo, and then click on the Generate button. We'll swap out our logo. And we can see here the table at the bottom contains all of our 21 different dimensions. At this point, we're going to go ahead and switch over to the scanning software and set up our scanning program. In the scanning software, we're just going to give it some basic moves to scan the geometry of the part. Once that data is captured, it imports into Geomagic. We can see how that single authoritative file is reused in the inspection software. Now we'll walk through setting up the 3D scanning program. We're going to be using an M3DI Pico scan that's mounted to a Mitsubishi Assista collaborative robot. And in addition, we have a single axis rotary table that the part is sitting on, so we can rotate the part around. The nice thing about the way the system is set up is that we don't need a safety enclosure because of the collaborative nature of this robot. And because the part is made out of aluminum and it's a finished machine part, the surface reflectivity, it may produce some noise. We've sprayed on a white spray to matte down the surface. The scanning software that we're using here is EOS 3D scanning software, and we'll go ahead and go into the project tab and start a new project. Click on the new icon, you can give it a name, click OK, go over into the automation tab, and in this case we're going to be pulling in a generic 12 rotation scan. So I can go ahead and open and load in my 12 rotation scan. You can see here in the program that we're going to be taking 12 scans in total, and then the system will automatically align, merge all the data together and set the stage for me to export the data into my inspection software. So at this point, what I want to do is connect to the robot. So I'm going to click on the icon up here to toggle offline to online, to hit the start button. What the system will do is it'll put the scanner in a position where it has the sharpest focus signal on the surface of the part. The system uses a projection system and a camera within the scanner to project a known signal onto the surface of that part. Because of the surface curvature and the features that are contained on that part, the signal actually conforms to the shape. And what the camera system receives back is a deformed signal. And so in essence, the system is sending out a known signal, it's getting back a deformed signal, and what's causing that difference is the surface curvature of the part. And so from that information, the system can calculate a very high accuracy and high resolution 3D reconstructed surface of that particular part. Now that the scanning is done, we can go ahead and go into the software and see our results. So we can see that we've captured plenty of data. All of the features are fully covered. And at this point, we can go ahead and export the data. So we right-click on the file name, click on Export, give it a name, save it in STL format, and click Save. Now we'll go ahead and import our scan data into our inspection project that was set up using the model-based definition file, and you'll see how the system automatically aligns the scan data to the CAD model based on the datums that we have set up. And then once that's done, it will extract all of the measurements that have been specified in the MBD file. In Geomagic Control X, now all we have to do is import our scan data. We're going to go up into the import function, choose our scan data, and select import only. Notice that the scan data comes in with its own orientation. This is almost always going to be the case. It's based on the orientation that the scanner was viewing the part. And so the first step that needs to be done is an alignment. And what Geomagic Control X will do is it will look at the scan data and the CAD file and automatically align the scan to the CAD. We'll go ahead and click the regenerate button. It will go ahead and make the initial alignment. Once that's done, it will calculate a correspondence, which is it'll extract the 3D points that represent a particular CAD surface. From that, it'll identify all of the datums and then extract all the measurements based off of the datums that are specified. We're reusing the model-based definition file that was created inside of SOLIDWORKS. That single authoritative file is again being reused in our inspection process. It's saving us a ton of time. We didn't have to recreate all of the geometric dimensions and tolerancing within Geomagic, which would be the typical process that I would follow if I had not had a model-based definition file. Very quickly, we have all of our inspection data updated, all of the measurements have been extracted, and we can now move on to exporting the data into our inspection report. If I bring up my report manager, I can click on the rebuild button, and if I scroll down, you can see that I have my updated measurements screenshot and then also my updated measurements table. So for each one of the characteristics, I have a tolerance range, I have my actual deviation, my reference nominal value, and my actual measured value. At this point, I can export this out in a number of different formats, either PDF, PowerPoint, or Excel. In my case, I'm going to go ahead and export this out as an Excel file. I'll save this, and here's the report opened up for me. On page 1, I have all my information about the part, the product name, inspector, the department. Page 2 contains the screenshot as we have it set up in our template. And then page 3 contains all of the measured values. Just like that, my inspection is complete. You saw how we reused that digital data to automatically set up our inspection process. Using model-based definition has really saved us a lot of time. We took that authoritative file that was created in SOLIDWORKS and we're reusing that data inside of Geomagic Control X to set up our inspection project. All we had to do was scan the part. That data was imported into the project, and Geomagic automatically aligned it, extracted all the measurements, and output all that data into our inspection template. And we're in a position now where we can go ahead and move this part over to shipping so we can get it to our customer.
It's important for your company to become an early adopter of using model-based definition. The reason for this is because the Department of Defense is already flowing down requirements into the industrial base to do so. Wherever you are, there are a lot of resources out there to help companies start their MBD journey. If you're not sure where to look, we're CCAT, and we're here to help.